Welcome back to part 2 of the chapter 2 tutorial. We're going to pick up with quantum numbers, and this is a slight departure from the first half of the chapter, but we'll still be in line with discussing the periodic table and its various sections, geographically speaking, because they will represent basically an address, if you will, for where we could locate different elements, as you've seen so far. And we're going to take that one step further and discuss quantum numbers, because quantum numbers are just a series of numbers and values that we will give that will serve as basically an address to where we can locate electrons within an atom. So just as we would give a street address of 1234 Main Street, and that would be an address to a building or a business, then we can also give a series of quantum numbers and they will serve as an address to electrons within a particular atom. And again, this is just for electrons because we know protons and neutrons, of course, are housed in the nucleus. So let's start by discussing the four quantum numbers. For quantum numbers, we'll begin with the principal quantum number, which is n, and this refers to the shell or the ring around the nucleus on which we have additional sub-levels where we can find electrons. Now, the shells basically have values of n, because that is the quantum number, n equaling 1, 2, 3, 4, 5, 6, all the way to 7. And this represents the 7 rows on the periodic table. So when we talk about the n value, that automatically references a particular row on the periodic table. So there's the first clue as to what the quantum number will tell us and where we're going on the periodic table. The second is the angular momentum quantum number, or L. This refers to the subshell, and of course the subshell will tell us about the shape of the orbital. Now what this will represent is possible values of 0, 1, 2, and 3. So L can equal 0, L equals 1, L equals 2, or L equals 3. Now one little quirk about the angular momentum quantum number is not just that it represents, let's say, a number such as 0, 1, 2, or 3, but it also represents a letter. And they mean the same thing. They're equivalent. So if we say an L value of 0, it's the equivalent of the S subshell. And L of 1 is the P subshell. L of 2 is the D subshell. And L equals 3 is the F subshell. And simply we have to have a number, because that's what a quantum number is. It has to have a numerical value, but we also have letter equivalencies to those numbers, and we happen to use the letters more so in writing electron configurations than we use the numbers. But it's important to know both, obviously. Now, what does the angular momentum quantum number reference on the periodic table? Again, it's going to reference a piece of geography on the periodic table, and this is going to reference four sections, that's one for S, P, D, and F on the periodic table. And we'll take a look at those below. Okay, now, 3 is the magnetic quantum number, that's M sub L. Therefore, it references, of course, the number of orbitals. And what this actually tells us is the values for the orbitals. Now, we'll talk about how many orbitals each subshell has, and of course, what those possible values will be at a later time, later on in this tutorial, or in the next one in part 3. But the M sub L values that can be present for quantum number M sub L are 0, plus or minus 1, plus or minus 2, or plus or minus 3. So we can actually have up to 7 different values for M sub L. There is no reference to the periodic table here, and we will discuss what orbital values mean in a different part of the lecture tutorial. So let's move on to number 4, which is the magnetic spin quantum number, M sub S. This refers to electron spin, and as you know, electrons are negatively charged and they're in pairs. So what this means is that electrons tend to be in pairs, and each orbital, which we represent as a box, as you'll see in just a little bit, is going to contain a maximum of 2 electrons, a pair of electrons. And because both of these happen to be negative, of course, because electrons are negative, they will repel each other. And how they repel each other is by spinning away from one another. meaning they'll spin in opposite directions. One will spin away in this direction, one will spin away in the other, and basically our spin numbers, or m sub s quantum numbers, can have only two. Regardless of what shell, subshell, or orbital you're in, your two electrons can only ever have these two values, which is plus 1/2 and minus 1/2. Plus and minus representing opposite directions, and the 1/2 meaning 1 out of 2, or 1/2 of the pair of electrons, meaning one electron spinning in one way and the other half spinning the other way. Simple as that. Now, what this references on the periodic table is a square, meaning one electron value. One square on the periodic table is one electron spin. So that means looking down here to, let's say, helium number 2 versus lithium number 3 versus beryllium number 4, you can see they just differ by a value of 1 square, or 1 electron. And so each space on the periodic table that you move from lithium to beryllium to number 5 boron to 6 carbon to 7 nitrogen and so on, that will actually be 1 electron, or 1 electron spin. So let's take a further look at this periodic table. And what this does is it references different sections, as we mentioned. So here we have rows, and the rows are labeled 1, 2, 3, 4, 5, and 6. And these rows, of course, represent, as this arrow up here indicates, the n value or shell value. The second quantum number, which will be L, that will represent your S, P, D, and F. So the first two tall columns, groups 1 and 2 here, all the way down where this one arrow shows you, those are your S section. Your P section starts with the remainder, 3 through 8, the tall columns. Groups 3 through 8 will represent the P section, as this arrow down here indicates. And the last section that we'll discuss is the transition metals, right here, the short columns that are in the middle, and those represent the D section. Now the F section we're not going to discuss in intro chem, but it would actually be the bottom section on your periodic table, the two rows, the inner transition metals, as we would call them, the lanthanides and the actinides, and those are your inner transition metals. Those would technically represent the F section, but we're not actually going to discuss those so much in this particular class. So again, we know that we have an S, P, D, and F section. So you may want to pause the video here and just jot this down, or just listen to the explanation, but this is something that it's highly recommended that you have in your notes. Again, we've looked at what the periodic table has to offer in terms of geography or territory. And if we treat this periodic table in terms of a map, or like a board game, if you will, we can say we're in the third row, so that is the N3. We're in this section of, let's say, magnesium, number 12. That will be in the S section, so this is technically 3S. And then how many spaces would we have to move within this row to get to magnesium? That's 1 for number 11, 2 to get to number 12, and there you go. You actually have 2 spaces that you've moved. So it would be a 3S section, move 2 places, and then we can write that in the proper format, which would be 3S2. Again, it's almost like a board game, but instead of rolling the dice and then moving 1, 2, 3, 4, 5, 6 down, through a row and finding your destination, so to speak, you're going to be given your destination. For example, 15, atomic number 15, which is P, phosphorus. You'll be given the destination, and you will be basically saying where you need to go in order to get there. Okay, I need to make sure I'm in the third row, which is an n equals 3. And of course I need to be in the P section because it's in the P section. So my L value will be equaling 1. Again, why is L equal to 1? Because we're in the P section, and technically up here, number 2, P is equal to L equals 1. And once I'm in the P section, I will have to move how many? Beginning with aluminum, 1, 2, 3, until I get to phosphorus. So it would be 3P3. And again, it's just looking at row, section, number of boxes. Row, section, number of boxes. This hopefully is a nice little outline of how the atom is broken down. And this is our nucleus, of course, with the protons and neutrons in the middle, and our shells. And of course we can have up to 7 of these, but I've drawn up to 4. And this would be, of course, n equals 4. So we're going to list all the quantum numbers that are possible here just for argument's sake and for practice sake. This is n equals 4, which means this is the fourth shell. It would correspond to the fourth row of the periodic table for the most part, which means that we have an S subshell, a P subshell, a D subshell, and an F subshell. So this is the shell, and then within the shell we have these subshells. All right, the L of 0 is the S, the L equals 1 is P, L is 2 is D, and L equals 3 is F. So there are our subshell values. Now, the number of orbitals that the S, P, D, and F have, okay, are basically going to be the following. And this is a typo here, so we want to make sure that we take this out. It should not be 6 orbitals for F, but rather 7, even though we don't really deal with F subshells in this class, but this should be 7. So for S we have 1 orbital, for P we have 3, for D we have 5, and for F we have 7. So 1, 3, 5, 7, odd numbers. As long as you can count in odds, you should be okay here. All right, next thing that you want to have is say, all right, now that the S subshell I know has only 1 orbital, what is the value for that orbital? Well, that means what is its M sub L value? The M sub L value is 0. And there's only one value because there's only one box or orbital. For P, we'll have 3 orbitals, okay? And the M sub L values that are possible will be, again, 0, and then +1, -1. We're just kind of working our way through the number line, if you will. D can have 5 orbitals, which means it should have 5 M sub L values. Again, we'll start with 0, plus or -1, or plus and -2. Again, that's 5 values. And last but not least is F. Again, we don't really deal with F, but just FYI, L equals 3 is F, and that means we have 7 orbitals. So this, again, should be 7 orbitals. So 1, 2, 3, 4, 5, 6, and there should be one more box that's 7. And in this case, we would have 7 different M sub L values, which is 0, plus or -1, plus or -2, or plus or -3. So there we go. We have all of our M sub L values now also assigned. The other thing, though, that is important to know about the S, P, D, and F sections in this class is how many maximum electrons can be accommodated in a particular orbital. So if you have 1 orbital, remember each orbital can have a maximum of 2 electrons. You may not have 2. You may not fill your orbitals to their maximum capacity, but it's important to know how many you can have so that you don't go over that maximum. So if each orbital is allowed 2 maximum, S can have up to 2 because it's got 1 box or orbital. This has 3, so we can put 2 in each, or 3 times 2 is 6. There you have your 6 electrons. Electrons here being represented by the arrows. 5 orbitals, which means 5 times 2, or 10 is maximum, 2 in each orbital. And of course, 7 orbitals times 2 would be 14. 14 total electrons maximum in the F subshell. So just basic information about the F subshells, which you need to know, is what I've described here, but they won't be part of the electron configuration, but it's important to know at least this part that we've discussed. Now, let's go back and discuss what these arrows are. These single-headed arrows represent electrons, and of course that's why there are 2 in each box, because electrons come in pairs, and there is a reason why they're in opposite directions, one pointing up, one pointing down. Remember that, again, electrons must have opposite spins, so one will be up, one will be down, and that is to conform to the magnetic spin quantum number, where one of those will have an M sub S equals +1/2, one will have M sub S equals -1/2. Now, which arrow is the plus and which is the minus is arbitrary at this point, but you should know that for each pair of electrons, each arrow designation that we have, meaning the spaces we've moved, that would be a +1/2 and a -1/2. All right, so let's move on to determining electron configuration. Please go ahead and review this section and the how-tos, and of course this section on how we will determine electron configuration and the format in which it is appropriate to write, meaning first give the row, then the section, and again notice we're using the letter designation, and then the number of spaces moved in exponential form. And then you can click on the second link for part 3, and we will then move forward and do some examples of how we can actually write electron configuration.